Okay, so sorry, we're going to start with a summary of lecture 3. Sorry, I think someone, did you want to say something, or I'm not sure who was talking, but anyway. So I'll start with a summary of lecture 3. In lecture 3, the main thing that we did was that we reformulated classical physics of particles and fields in the language of action principle, least action principle. The starting point, the hero of the game, is a functional, which is mapped from smooth functions, we call them fields, right, to say real numbers. Action could be real, could be complex. Most of the time in physics, it's real. Complex actions have very particular meaning. So it's a map from the space of field configurations, right? Every function, smooth function, is a field configuration, right? To numbers. That's what the action is. And we said that we're gonna use the principle of locality in the following way. What was the principle of locality? This functional is an integral over space-time of an integrand that is defined at a point, at any point, right? So, and that integrand we call the Lagrangian density, right? This was the principle of locality. This was a key intuition that we borrowed from classical physics and generalized, right? Turns out, well, with some tiny caveats, almost everything we see around us are local theory. Locality is a very key principle in field theory, and that's what makes it easy. Of course, as you go to higher dimensions, this is more restrictive. That's why field theories are more restrictive than quantum mechanics, which is 0 + 1 dimensional field theories. All right. So, what was the point of this action? Functional. It was action principle, which says that the functional derivative, the variation of the action with respect to the field configurations, is 0. This is just a statement that the path that the particle takes, or the solution to the equations of motion, the field configuration that actually occurs, is the one that minimizes the action, right? And we discussed in a little bit more detail what it meant to take to differentiate, to do differentiation for functional. So these are two key concepts that we're generalizing from calculus of functions to functionals. We discussed differentiation, how to generalize it to functionals. Now integration is we're gonna generalize sometime later in the course, and that's gonna become functional integration, otherwise known as a path integral. That's what a functional integral is, right? So all we were doing is that we were doing calculus on the space that is the space of function, on functionals, right? We're doing calculus for functions. We'll get there, right? I will have some comments about the first appearance of any path integral or functional integral is going to be the end of this lecture. We're not going to discuss it in detail. It's just going to be a single example. All right. And then using the variational principle, we said that if the Lagrangian density doesn't have an explicit time dependence or space-time dependence, explicit space-time dependence, meaning that there is no x nu here, then the equations of motion, we just derive them, and they're given by this Euler-Lagrange equations, right? So the discussion of the last lecture was somewhat formal. Today, what we're going to do is we're going to discuss 4 examples. So 4 important examples of classical field theories, and look at this equation and how it evolves, right? What's the physics of it? The whole discussion today is going to remain classical, right? The first example, each example, I try to make a very sharp point, and I'll try to summarize what is the point of each example. Example 1 is going to be massive relativistic 3-scalar field, right? Example 2 is going to be free boson field, but non-relativistic, right? example 3 is going to be classical electrodynamics. This is Maxwell theory, right? Electromagnetism. And then the last example is going to be statistical field theory. This is where I'll try to tell you guys about this deep connection between statistical physics and quantum field theory. So the punchline of the example 4, which we're just going to touch upon and move on. I taught a third of a course on this topic before a year ago or 2 years ago. It's the statement that even if you don't care about quantum mechanics, you want to study classical physics, phase transitions, classical phase transitions, you still have to learn quantum field theory. This is through the classical quantum field correspondence. So there is a correspondence between classical fields and quantum fields. Well, we'll get there. All right. Any questions about the last lecture, about what we're going to go through today? All right. So let's start with example 1, massive relativistic scalar field. So I just want to point out the term scalar, we defined very briefly what it is. So recall the definition. It's a statement about how this function, this object transforms under Lorentz or Poincare transformations, right? Every time you say the word scalar, that's what it means, right? We'll spend a lot of time on this and discuss what it means to talk about representation. So it's all about scalar representation. All right, so what's the functional we're going to start with? The Lagrangian. Because I'm going to assume locality, right? So I don't need to write these integrals over space-time. I'm just going to write in terms of, write down the Lagrangian density, right? So the Lagrangian density is going to be a function, a map from the field at each point and its derivative to real numbers. And I have at my disposal, I'm going to do it relativistically. So I have my disposal flat space metric. All right, this is the functional we write down. So you could check for yourself that each term is individually Poincare invariant, right? So actually, sorry, the action is Poincare invariant. You could check that. And sort of there are limits to what you can write. We might get there in this course or not. There is a rule and general philosophy to why we write these expressions. There are basic principles that we actually discussed in a course on renormalization group in the past, but these actions are not random. It's not just something I write down. Well, you could view it as something I write down that describes something particle in nature called Higgs. But you could also view it as more as a grand point of view. You could say, what are all the theories that could exist, right? And then we might or might not get there to discuss what these things are. But one thing that's clear is that whatever you write down here, if it is to have an interpretation of local relativistic quantum field theory, it better be interpreted in terms of a Lagrangian density, and the expression better be, or the action better be Poincare invariant. We'll get there. So recall what Poincare transformations are. There are just rotations and boosts. This is the Lorentz group plus translations, space-time translations, right? So if I just use the standard good old coordinates of space and time, do the splitting of space and time, this action is basically phi dot squared with a half minus the gradient of the field phi squared, right? And there could be a potential here, right? Here, in this case, the potential is just master, right? What's important is that this is the kinetic energy density, right? So the terms, if you recall from classical physics, there's the energy minus potential. That's what Lagrangian is supposed to be, right? As opposed to Hamiltonian where you add them up, right? So that this minus sign is already implemented in this convention. All right, so what are the equations of motion? Well, we're not gonna start with the action anymore. We did it once and forever. We wrote down the Lagrange equations. We need to write down this equation. Well, let's take a derivative, functional derivative of Lagrangian with respect to phi x. This is the very first term. The second term is this. You put them together, you get this celebrated Klein-Gordon equation. So let's recap. What is this? This is supposed to describe the dynamics of a scalar free field, massive free field, right? This is a field theory, but classical. At this point, we're just doing classical physics, right? So this is a function of space-time, and as in space-time, it will fluctuate. It will, well, sorry, classically there will not be fluctuations, but there will be solutions to these equations. Good. This is called the Klein-Gordon equation. So sometimes you see this convention of plus here is because I'm using this convention that is +1 minus -1. Some books use a different convention, so they put the minus sign over there. All right. So what are the solutions to these equations? The solutions are pretty simple and physically very, very reasonable. Well, very intuitive. This is the equation you have. Recall how this is a linear theory, right? Recall how we solved our Gaussian model, simple model in the case of the sound, the field theory of sound. All we did was that we did a Fourier transform. So we're going to do a Fourier transform in space and time, right? So frequency, omega, is the Fourier transform of time, and the vector k is the Fourier transform of x, right? This is like wavelength. All right, when you Fourier transform it, it becomes an algebraic equation, right? Which this is trivial to solve. It basically, the solution to this is any wave equation of this type where omega k has to satisfy this dispersion relation, right? As long as omega k, and as long as you have this dispersion relation, the first term vanishes, right? This term vanishes. Therefore, your equations are satisfied. This dispersion relation is sometimes called the on-shell condition, right? This is the solution to the equations of motion. So what is the physics of this? The physics of these waves, these plane waves, all the Gaussian models we write down are just the solutions of them that are going to be plane waves. And the only freedom that is left is just dispersion, how omega is related to k, right? How energy scales with momentum. In this case, so these are waves that are propagating in space-time, right? So if this is a wave, there will be some sort of momentum, it will move along, and the energy that it will carry will depend on the wavelength, right? This is the on-shell condition, and it decides the dispersion relation. Good. All right. In relativistic notation, I can write this down as p mu minus m squared equals 0. This is important because later on we'll write this down. I'll write down this equation a lot, right? So this is the on-shell condition. What this tells you is that if you recall from, so we're doing classical physics, but if you recall from the particle wave duality, right? There was a relation between momentum and energy, between momentum and wavelength, energy and frequency. You just multiply them by h bar naively, right? And if you do that, you get you could interpret the dispersion relation as a relation between momentum and energy, right? Now, the solutions to this dispersion equations are, if I'm in 1 + 1 dimensions, if I'm in 2 + 1 dimensions so that I can draw it, right? Are these hyperboloids, right? They're called hyperboloids. These guys, right? These are the solutions to that. There are two of them, right? You have to be on these hyperboloids. So all I'm doing is I'm plotting this, right? The upper, the positive frequency ones, the positive frequency. So what I'm plotting are these two plots, right? K squared plus m squared. There is a positive frequency. This is positive frequency, and then negative frequency modes, right? Both of them solve the equations of motion. So you could check that the negative frequency modes still have positive energy. And that's just because of the fact that the energy is like, well, you can check that, right? So to check that, you just write down the Hamiltonian. All right. Any questions so far? Actually, let me just make a quick comment about adding interactions, and then I'll pause.
So this was a Gaussian theory. This was Gaussian means it was just like proportional to phi squared. It had two insertions of two order. It was order two in field phi, right? The Lagrangian density. If you which means that as you vary with respect to phi, your equations of motion are becoming linear, right? You start with two phi's. That was your functional. You vary with respect to phi. That kills one of them, right? And your equations of motion are going to be some differential operator acting on the field phi, but it's linear in phi. Why is this important that the field is linear? Can anyone just say a one-liner? Why is this important? And from partial differential equations, do you recall what was the importance of linearity?
You can superpose them, I guess.
Yeah, you could add solutions to get new solutions, right? Therefore, you can classify the space of all solutions by just writing down a basis. They form a vector space, right? And actually, I've already written down an orthonormal basis for this vector space, right? And I haven't told you what the inner product in this space is, but there is a canonical inner product. There's a vector space. You could turn it into a Hilbert space, and I will actually have a comment about this Hilbert space, right? But the linearity is important because it's a method it's a method where you know actually how to classify the space of all solutions to classical equations of motion, right? Because they just form a vector space. Now, the moment that you add an interaction, right, say lambda phi 4 with some coefficient, your equations of motion are going to change this way, right? This is the interaction term. The interaction term introduces nonlinearity, right? So even if you're lucky to find solutions to this equation, it's very, very hard, if not impossible, to classify all solutions. First of all, even if you did classify all these solutions, there is no vector space structure to them. There is no simple way of adding and subtracting them, right? Even worse than that, you can't even multiply these. So yeah, anyway, it's not a vector space. It's not a vector space. That's all I was going to say. So what is our approach? In the presence of interactions, all we can do is, well, one of the things that we're going to do is doing perturbation theory in lambda, right? And construct solutions order by order in perturbation theory in lambda. This is a usual trick that we do. And as we quantize, so this is a classical business, this is classical field theory I'm discussing. Doing the same perturbation theory in quantum field theory is organized in this nice pictures. They're called Feynman diagrams, and that's going to be a huge part of this course. But all we're going to be doing is just going to be perturbation theory in this. If we could solve this equation exactly, we would never be doing this. Even if you could solve this equation exactly, there will be some issues, but that's a little bit different thing. So when I was saying, when I was saying that that sometimes the theory is strongly coupled, right? So when lambda is small, when you organize your perturbation theory, each of these guys will have an interpretation of a particle, these basic waves, right? The basis, right? And they will go along and interact and do all sorts of things. But when lambda is large, there is simply no nice connection between the space of solutions and the solutions with lambda equals 0. There's just simply no nice connection. That is what it means to have a strongly coupled field theory. That's why they're hard, they're difficult. It boils down to the problem in differential equations. All right, any questions? If there are no questions, let's move on to example number 2. So I have a point. I tried to make a very sharp point. You're supposed to be a little bit confused about example number 2, 3, and 4. In the whole course, I'll try to just fix these things. I'll not make any wrong statements, but I want you to think about various aspects of what we do. So now what we're going to do is that we're going to pick a non-relativistic complex free boson. What is the point of this? The point of this is that it's going to be a first order Lagrangian, first order in time derivatives. So we'll see that.
when you are dealing with derivatives, right? Relativity, Poincare invariance, tells you that if you want to construct a term out of the derivatives, this is sort of the construction. The second order term you could write down using the derivatives. This is pretty much all you can write down. You can play with this, but this is all you've got. But when you say, I don't have relativity, I only want to stick to rotation invariance, right? In space, and I'm going to treat time differently. Now there's a new set of terms that are allowed, right? So the fact that you have rotation invariance forces you to write down the spatial part of the derivative, Laplacian. This term has to be basically, this is fixed. You can't do anything with this. You can't mess with this. That's rotation invariance, right? So what we're doing is breaking boost. But now, because there's no nice connection between time and space, I can write down whatever I want here. So for example, I wrote phi del t of phi. Does anyone know why I wrote phi del t of phi and not phi del t to the power of 15 of phi? What's the difference between the physics of the two?
I guess translation variance in time.
No, that's not an issue.
Okay.
So here's a hint: Fourier transform it. Right? This one has the first order is proportional to omega. This is proportional to omega to the power of 15. If I'm looking at low energy, which one do I care about? Omega. Right? This is just every time we get these confused about these things, all that we're really doing, a lot of these terms that we're writing are the most general things that we can write down that are consistent with the symmetries and are low energy, low frequency, low momentum, right? These are the principles. This is actually one of the basic principles of quantum field theory we could discuss another time. All right, that's why I wrote this down. All the other terms I could write down are suppressed deep in the infrared. In long wavelength, they are irrelevant. Well, I shouldn't say irrelevant. They are not important. Okay, good. All right, so what's the action I'm going to write down? The action I'm going to write down is going to look like this, right? So when I Fourier transform it, I'm going to get omega minus k squared times 5 omega k equals 0. So my solutions are still going to look like plane waves, but the point is that now I have a non-relativistic dispersion. Energy is like p squared, right? As I expected from classical physics. This is sort of the origin of why energy is p squared and not p to the power of 15 or p to the power of 2 over 15, sorry. All right. Okay, so good. Is this point clear? Now that I've broken, now that I don't care about Poincare Lorentz invariance, right? I get to do a little bit more. I don't have to stick to scalar fields. I can pick things that are scalar with respect to spatial transformations, right? But they could do crazy transformations with respect to space-time. So the point of this example I give is twofold. You'll see. First is this. Imagine I have two fields, phi 1 and phi 2. I'm just going to add them with putting an I in the middle. It's a complex field. It has 2 degrees of freedom, 2 real degrees of freedom, but a complex field, right? Alternatively, I can write down everything, organizing this field, complex field, in terms of its real and imaginary component, and think of it as a vector. But this is not vector in the sense of how it transforms under space-time transformations. That's very important. The fact that I wrote it this way, it's an arbitrary organization of the degrees of freedom in my head, but this is not a vector field with respect to space-time transformation. The scalar, vector, and spinors with respect to space-time transformation, those are very meaningful concept. This is arbitrary if I want to put them in a vector or write them as a complex field. Good. So now I have to write down an action for phi1 and phi2, but just because I want to make a point, I'm going to write it in terms of the complex field and its conjugate, right? There are 2 degrees of freedom. I can think of it as the field and its conjugate. All right. So what is the action I'm going to write? I'm going to write the following action. It's going to be first order in dt, right? As I promised, because it's going to be non-relativistic. And then I'm going to add this del phi square term. I put an I here because I want the action to be real. That's why I put an I. Let's stare at this for a second. Nobody complained before about dimensionalities. But here, you notice that when I have first order fields, so first order in time, sorry, in my action, I have terms that are first order in time, derivatives in time. If I want to put them next to del phi, I need the dimension full parameter here. Right? Nobody complained about that, and I wasn't expecting any complaints. What is that dimensional full parameter? It's 2 over m here. Okay, so this guy has the dimension of length or inverse mass. You could think of it as 1 over mass, where mass is the mass of classical physics. All right, any questions so far about the action? It's an action I just wrote down because I can. It's real, it has all the nice properties that I want, and it's first order in del t, and it's second order in so it respects rotation invariance, it's low energy, it's all good. Good. All right, so let's write down the equations of motion. The Euler-Lagrange equation. This is the result of the Euler-Lagrange equation. Well, you basically do your derivatives. It's pretty straightforward. You only need to find the variation with respect to phi star, because the variation with respect to phi is just the conjugate, the star of that, complex conjugate of that. You do that for both of them, and you basically get the equation of motion. I will not, you can do this at home. I just wrote it down if you want to go through them quickly in your head. All right, so what do I get? I get this equation of motion. Does this equation of motion, does it look like something you've seen before? It looks like Schrodinger equation, right? It has an I, del t. It has a phi. If phi was, if I was replacing phi is a function of space time, right? If I was replacing phi with the wave function of a particle, this would be identical to that. A, as I said, has the interpretation of 1 over m, 1 over mass, right? It looks like the Schrodinger equation for a single particle, except that it's not. So actually, the analogy goes even deeper. You might complain, where is the h bar, right? So recall when I was putting h bar here, omega, so here I have to put 2 powers of h bar next to k and 1 power of h bar next to omega. If you keep track of that h bar ends up here in the Schrodinger equation in the right place. But I'm working units where h bar is 1, so I don't care, but it's taken care of. H bar is dimension full, so it won't mess with, I mean, it's going to work out. If the question came out correctly, it's going to be correct. All right, so it looks like Schrodinger equation, but they are very different. They are very different, but interestingly related. I made a comment that was intimately related to this when we were doing the second quantization of the phonons. When we constructed the Fock space, we looked at the single particle Hilbert space. I pointed out that the single particle Hilbert space looks like the solution of Schrodinger equation. So the statement I'm making, here has a similar flavor. We're eventually going to come back and clean up all of this and tell you what is going on. But these I guess, similarities between these the equations and Schrodinger equation are not accidental, but they're not identical either. They're not the same thing. So just to be very clear, what is important? It's important that equation number one is the equations of motion for classical field. There is no quantum in there. There's absolutely no quantum in there, right? Whereas equation two is solution for, it's just equation of motion for quantum mechanics, a Schrodinger equation for wave functional, right? So this psi squared has interpretation of probability, whereas this phi has no probability in it, right? At least naively. All right, so I said this before. Here are the solutions of plane wave, and you have the dispersion. What is important compared to the relativistic case where we found positive and negative frequencies? Here you only have positive frequencies. There are no negative frequencies here. Sorry. All right, very good. So let me summarize this. I guess let me just try to make this provocative statement that I made a little bit more rigorous. For those of you guys who want to think about this, I absolutely invite you guys to think about this. The space of solution, what we did was that we looked at the space of solutions to the equations of motions, right? That thing in physics has a name. It's called phase space. Because the equations of motion were linear, phase space was a linear vector space. I already wrote down an orthonormal basis for it, which means that I had an inner product. I had a sense of, I had a measure of saying, or like what's the angle? I had a definition of angle for these vectors, right? Once you complete that vector space with this inner product, you obtain a Hilbert space. This is the Hilbert space of classical solutions to the equations of motion. This is phase space realized as a Hilbert space. There's no quantum mechanics in there. But it's still Hilbert space as a vector. It's still a vector space with an inner product. Now you also have the Hilbert space of a single quantum particle, and they happen to be the same Hilbert spaces. That is the origin of. Well, that's what I'm going to say. Right? One side is classical, one side is quantum. All right. Any questions about example number two?
In the phase space, you mentioned what's the difference between the phase space and the trajectory on that phase space?
Oh, so to pick a trajectory and a phase space, all right. Well, you have to pick a Hamiltonian. Hamiltonian. Now I'm describing to you a little bit more about Hamiltonian dynamics, Hamiltonian formulation of phase space formulation of classical mechanics. So flow, what points in the phase space evolve along the integral curves of the Hamiltonian. So you have a phase space, you have a Hamiltonian, it's a function in the phase space. That function will have integral curves, flows that preserve energy, preserve Hamiltonian, and flows along those integral curves of Hamiltonian are actually the equations of motion. Yeah, that was too quick. That's just something you could look up in your classical mechanics. Yeah. All right. Any other questions? So in recap, we went through two important examples: relativistic massive scalar field and non-relativistic complex free boson. Each of them we had a point. These are classical theories. We're just doing this class. We're doing classical physics. We're writing down Euler-Lagrange equation and looking at the solutions. We saw that the dispersion was different. We saw that in the relativistic case, we had positive and negative frequencies, whereas in the non-relativistic case, we only had positive frequencies. We saw that there was some, well, okay, that's where I'm gonna stop. All right. Questions?
Okay, so the space of you meant the space of solution to equation of motion of the classical field. Are these solutions you take the the fields at fixed times. Because
No. Solutions are space-time solutions. These are
so they're not at fixed times.
no, they're functions of space-time.
But from my understanding, the Hilbert space of a single quantum particle is consists of like wave functions that only depends on a space. And when we talk about wave functions that depends on time, we might mean a trajectory on that Hilbert space.
Okay, we have the Schrödinger equation that tells you how the wave function evolves as a function of time. So the solution to the Schrödinger equation is a wave function of space-time, right? How
Yeah.
the wave function evolves as a function of time. And I'm comparing the space of solution to Schrödinger equations, which are particular functions of a space and time, to solutions to the classical equations of a field in space-time. They both have the right dimension. They're both functions of the same thing. They're both functions.
Yes.
Yeah. But the point that you're making, which is totally valid, is the interpretation of dynamics. So dynamics, when you're working in space-time coordinates, could get very confusing, and often to make sense of it nicer, we go to the phase space. But yeah.
Okay.
All right. Any other questions? Let's go to example number 3. By the way, these examples we're going through, I repeat, they are not arbitrary. These are the examples we're going to go through are, with the exception of fermions, because you haven't learned about what a fermion is. Pretty much every single one of them is every single field theory you would care about in this course, except for one, which is fermions, and we haven't discussed them yet. But these are important field theories. Now, what we're gonna do is that we're gonna do electrodynamics, which is the field theory of electromagnetism. I don't know when was the last time you took electromagnetism, or whether at all you took advanced electromagnetism Jackson's level. It won't matter. I'll do a review of electromagnetism for you. Hopefully you remember Maxwell equation. That's what I'm gonna assume that you guys can all remember, right? So you have an electric field, E, you have a magnetic field, B. These are vectors in space and time, I guess. Space, right? There is charge density, rho, right? And then you have current density, vector J. Good? And I'm using in notation C is equal to 1, speed of light is equal to 1 for this whole course. Often H bar is equal to 1 as well. Okay. All right. So what are Maxwell equations? Well, if you remember, this was Gauss's law tells you that the divergence of E is a charge density. Then there's a similar equation for the current, but that will tell you that this is the second equation. I'm just not going to read it. You hopefully remember. Then there are these two more equations, right? The first two equations are important, are different from, so equation number 1 and 2 are different from 3 and 4. Equation number 1 and 2 are sourced. They are coupled to charges, charge and current, whereas equation 3 and 4 are not sourced. They're not coupled to any charges, right? These are just some relations that the E and V will have to satisfy. These are Maxwell equations. So if you, I don't know if you remember from your electrodynamics, but energy carried by electromagnetic wave is E squared plus B squared. And if you try to write down a Lagrangian for it, it will look like E squared minus B squared. Okay? So compared to what we've been doing, if this is the Lagrangian density, we should be able to write it as the time derivative of something squared plus space derivative of that thing squared, right? And this is something that we already do in electrodynamics. Even if we define the scalar potential phi in the following way and the vector potential in the following way, right? These are, so now this variable A is the thing that is time and space. So A and phi are things that as time and space derivatives are related to E and B. So with the right, there's a chance that if with the right, if you rewrite this equation in terms of A and phi, it looks like the good old action that we want. Right? Okay. But this we'll see that the rewriting will work, but there is a catch. This A and phi degrees of freedom that we introduced. So these were physical. Everything that was physical was here, right? I listed them. This A and phi, I just made them up. I made them up so that I can write down a Lagrangian density that looked like the stuff I recognize. All right? This is important. But when I made them up, I also introduced some stupid redundancy. Right? If you shift phi to phi, if I pick an arbitrary function of space-time, alpha, and shift phi by time derivative of alpha and vector potential by spatial derivative of alpha, my E and B, from these two equations, it's obvious that E and B don't change. So the vector field A and phi, they represent my E and B, my physical degrees of freedom, but they have some extra junk in there that I just introduced by hand. Right? That is gauge redundancy. It's not the symmetry. I'll make sure that none of you guys get confused about this. It's sometimes colloquially called a symmetry. It's not a symmetry. It's a redundancy. It's a stupid redundancy that we introduce. I'll tell you later why we introduced this redundancy. But at the moment, it's pretty clear why, because I had a Lagrangian that I wanted to write down as the derivative of something, and time derivative and space derivative of something, and this was the rewriting came up with. There might be some other degrees of freedom I could introduce that might or might not have redundancies. Okay, but let's go with this, and I'll try to make a point here. All right, is this one clear? So there is absolutely no physics associated to this shift alpha. A and phi describe my physics, the physics that I'm trying to describe, but also they have some imaginary stuff in there, like that I've made up, right? And they're not physical. I have to always make sure that those stuff that I made up I'm not using them to describe physics, right? It's a redundancy. That's what gauge redundancies are. Are there any questions about this? So two different values of the vector field A that are different by this shift, the gauge transformations, are describing the same physical state. They're not describing different things in physics, right? That's the sense in which they're redundancies. All right. So, so we said that this, oh, sorry, I think I forgot. So we often package phi and A as a 4 vector, or yeah, for the purpose of example 3, let's stick to 3 + 1 dimensions. The story will be different in different space-time dimensions. This story, previous story was general. So this is my 4 vector, A mu. Now let's define a field strength in the following way. You just take a derivative with respect to mu and then mu, and you anti-symmetrize, right? There's an anti-symmetrization. Now, what's neat is that this guy is gauge invariant. You could check it by explicitly shifting things. Or more directly, you could just write down F mu nu as a 4x4 tensor. This is what it is. You can clearly see that every element in there is just either elements of the vector, electric vector field, or the magnetic vector field. But it's just a packaging of my degrees of freedom. And then similarly, I'm gonna introduce J mu, which is the 4 current, so vector current. And I'm putting the current density and charge density next to each other. This is the time component. Now it's straightforward to see that this is something to check for you guys. Maxwell equation number 1 and 2 that had J mu and rho sources on the right-hand side could be written elegantly in the following form. It's a very elegant expression you can write. Okay, very good. Now, this formulation that we just wrote down comes with a bonus. If you take a derivative of equations of motion with respect to nu, you end up with the derivative del nu of j nu. But because these two partial derivatives are symmetric and f mu nu was anti-symmetric in mu nu, this has to vanish. Therefore, del mu j mu has to vanish, which if I write down, is going to be the time derivative of charge density plus the divergence of the current density should be 0. That has a name, charge conservation. So I got charge conservation for free. Well, I didn't really get it for free. I sort of designed everything such that it works. But the anti-symmetry of, and the fact that f mu nu was anti-symmetric in mu nu indices is what bought you charge conservation. Is it good? Yeah. All right, so those are my equations number 1 and 2. I still need to work out the 2 other equations. So these are 1 and 2. You could check for yourself at home that these 2 equations are what I wrote down. So I have to make sure that equation 3 and 4 are satisfied. Turns out they're already satisfied. They're automatically satisfied. So all that I'm dealing with is just the equation I already wrote down, but you'll see that in a second. So to make this point very clear, let's talk about 3 plus 1 dimensions. Anti-symmetry of f mu nu already implies equation 3 and 4. So this is a very nice package, elegant package way of packaging things. So equation 3 and 4 of Maxwell equations could be written as in the following form. It's the derivative of f mu nu, but you use this totally anti-symmetric tensor in 4 dimensions, right? To just contract indices. And you could make sure that you could check this because this because of the anti-symmetric properties of f mu nu, this is 0. So equation number 3 and 4 are also implied by anti-symmetry. It was very crucial that f mu nu was written in a way that was anti-symmetric. Also, anti-symmetry is what made sure it was gauge invariant. If you write this down, the first term has a transformation, the second term has a transformation, and the minus sign in between them makes them cancel. That's why f mu nu is gauge invariant, as anything physical should be. So I'm pointing out a lot of things that I think in your spare time you should go through. If you want to understand what's going on in field theory, you have to do these exercises for yourself and decide. But we won't have time to do this every single line in class. That's perhaps what makes field theory a difficult course, but I absolutely recommend that you keep track of these steps one by one. All right, so here I want to point out something, a deep statement. We won't be using it in this class much, but I want to say it because for those of you guys who, this might come up in some research work that you guys do. I can take an f mu nu and contract it with totally anti-symmetric tensor in such a way that was suggested by this equation. By the way, this equation is called Bianchi identity. And call this the dual tensor. F tilde is now a two tensor. It's a dual tensor. I'm going to call it the dual field strength. Now, Bianchi identity, this Bianchi identity looks like Maxwell equations without sources written for the dual field strength. So let me just say it now, we might not come back to this ever again. The origin of this is this is electromagnetic duality. In electromagnetic duality, the broad idea is that there is a transformation. You could check that, actually. I'll say it explicitly. If you swap electric field and magnetic field, if there are no sources, nothing in the universe changes in the absence of sources. However, in our universe, things change. This is not a symmetry. And that is because we have electric charge. We have electric charge, but we don't have magnetic charge. We have electric monopole, right? A single charge that sources electric lines that come out, but magnetic lines cannot end on anything, right? So there's no magnetic monopole. Therefore, there is no transform duality. There's no, it's not a symmetry. If there was no electric charge or magnetic charge in the environment, then there would be, this would be symmetry. Anyway, I just wanted to say that. All right. So this actually, oh, sorry, I guess I did not say this. No. I can now that I have my vector, my f mu nu and this a mu, I can write down the most general term, which is Lorentz invariant, gauge invariant, parity and time reversal invariant, and it doesn't have any more than 2 derivatives. This is it. You can't write anything else. This is what's beautiful about field theory. It's inevitable. It's forced on you. And we go out there and we discover theories. Of course, this was after the fact that we knew about light. But now, what is important here is that both terms are local. So it's a local theory. Very good. The first term is gauge invariant. It's written in terms of gauge invariant objects. The second term is not written in terms of gauge invariant objects. The action, the contribution of this term to the action is gauge invariant after an integration by parts and using the conservation of charge. You could check that. You absolutely should check that. But the Lagrangian itself, we did not write it in terms of carries a bunch of this imaginary stuff I made up. All right, let me tell you the lesson. This comment is too quick for this discussion. It's a big conversation, but the reason we introduced these imaginary gauge redundancies is because we wanted to write down a local action. It's the price we paid. These imaginary redundancies, these made-up redundancies, are the price we had to pay to write down a local action. There is, in other way, there is a very special form of non-locality imposed on you by conservation of charge. That was a comment I'm gonna make, and I'm gonna leave it at that. So we do this in physics a lot as well. Sometimes there are very special forms of non-locality, and we arrange for them by gauge redundancies, for instance. That's one way to do it. It's not an arbitrary, wacky non-locality. It's a very, very special form. But again, we insist on the local degrees of freedom. Yeah. All right, very good. Okay, so if you take this functional, now the action over this, integration over this, and vary with respect to a mu, because now your a mu is your dynamical degree of freedom, supposedly, is your field. Then you get this equation plus boundary terms. You set the boundary terms equal to 0, and you get Maxwell equations. Everything is good and nice. This was the right action to start with. The electromagnetic duality that I mentioned is that if you set the source equal to 0 and send E to B and B to minus E, this is the symmetry of Maxwell equations. You could check that. That's a cheap method actually for writing down Maxwell equations. If somebody asks you to write them down, you have to make sure that under this symmetry, what you've written down is symmetry. The symmetry swaps the charge and its dual. I said what I said. I'm not going to say anything beyond that. All right. I said this already, but let me repeat it. Why did we introduce a mu, even though it has unphysical redundancies? It's because we wanted to insist on locality. The reason is that we could not write down a Lagrangian that was local and had only gauge invariant terms that could reproduce the correct equations of motion coupled to current charges. This is the reason. If tomorrow you come up, in this case, we do know that this is not possible, but if one of these gauge theories, if one of you guys comes up with a way of a change of variables that will make everything manifestly gauge invariant and local, that tomorrow that theory will be named after you, and starting tomorrow we'll forget about the gauge degrees of freedom. This is like a it is a game you could play actually, but I mean we already know that this is not possible in simple gauge theories that we're going to discuss in this class. All right, so locality and gauge invariance are intimately related. But I repeat, this was all made up. This is gauge redundancy was made up, introduced by us as a bookkeeping method because we just wanted to work with local stuff. All right. Any questions? How are we doing on time? Now, because it was a redundancy, we could also fix it. Because we said that transformations that are related by this values of the vector field, a mu, that are related by this gauge transformations are physically equivalent. So we might as well just fix them. There are various ways that you could do this that could be convenient for some ways might be convenient for one calculation, some ways might be convenient for another calculation. But here, let me just give you some of the very famous gauges that we usually pick. If you write down the action, there are no time derivatives of A0. Is it obvious to everyone? Do you know why? Why is there no time derivative of A0? All right, what was F mu nu? It looked like del mu A nu, right? If you have time derivative of A0, that looks like F00. Didn't we say that's anti-symmetric? Well, said differently, the anti-symmetry will make sure this is not there. All right? Good. So there are no time derivatives of A0. This tells you that there is no canonical conjugate associated to A0. So if you want to go to the Hamiltonian formulation, this is confusing. There's no canonical conjugate momentum. There's no dynamics associated with A0. This is just a constraint. Of course it's a constraint. It was a made-up degree of freedom. We made it up, and this constraint is the thing that we have to satisfy to make sure that we don't interpret this made-up degree of freedom as something physical. So one way to fix it is by fixing A0 to A of t to be, for example, actually, sorry, how do I want to say that? No, sorry. One way to fix it is to take a vector field, 4 vector field, contract it with A mu, and set it equal to 0. Now, if you pick something n mu that's space-like, this is a gauge that's called axial gauge. If you pick it to be light-like, this is called light cone gauge. If you pick it to be time-like, it's called temporal gauge. Depending on your calculation that you're doing, one of these gauges might be more convenient. But what you're doing is that you're basically setting to 0 a non-dynamical degree of freedom. A made up, well, it's not a degree of freedom, it's a non-dynamical made up thing. There's another convenient gauge you could use, and it's called Lorentz gauge. If you take F mu nu and if you look at the equations of motion, sorry, let me just make one, well, okay, never mind. Well, we're going to come back to this gauge, and you'll see that using the right gauge and the right calculation can help you a lot. So if you look at the equations of motion and write the equation of motion in terms of A mu, it looks like this. If I set this term to 0, this looks like 4 decoupled scalar fields. Well, not scalar, 4 decoupled Klein-Gordon equations. It looks like 4 decoupled Klein-Gordon equations, right? How can I set this term to 0? By saying that del mu A mu is equal to 0. That's Lorentz gauge. so that the equations of motion becomes like Klein-Gordon, massless Klein-Gordon equation with one extra vector index, right? So in the Lorentz gauge, I just can easily write down the solutions to the equations of motion, right? Without any extra work. What are they? Well, it's just basically the plane waves that we had. It's massless, it's relativistic. Here is the dispersion, right? And because there's a 4 vector worth of it, I can put this. Oh, sorry. Yeah, I can put an arbitrary function over here. This function is called a polarization vector. That's literally what the polarization of light is. Now, because this was the gauge you picked, Fourier transform of it will tell you that you have to have this satisfy this equation, right? This is the gauge condition in the Fourier space. Does anyone know what this is? All right. If you haven't seen,
The polarization is always perpendicular to the travel, right, to the momentum.
no. Yeah, this is something that you probably have learned about if you took Jackson or any electrodynamic course. But yeah, this is a polarization vector. All right. For now, this is the end of example 3, right? And this is as much as I'm going to say for classical electrodynamics. We're going to come back, quantize it, do all of that, right? But recall, we're going through a few examples, key examples of the action principle for theories, classical field theories we care about. Everything we're doing is just classified at this point. And I should repeat, every single example is there for a reason. In this example, what we wanted to make very clear is this redundancy, gauge redundancies. Do not use the term symmetry and gauge together in the same sentence. It's all terminology is incorrect, it's redundancies. But what's nice is that polarization, and this is a theory of light. This is a theory that there are massless excitations. They propagate in space-time as free waves. They do not interact. Photons do not interact, self-interact, right? And they have a polarization. They carry polarization. All right. Good. Okie dokie. Example number 4. Any questions about electrodynamics, ED, before we get to QED later in this course? Okay, example number 4 is perhaps deeper than all the other 3, and might confuse you as you could spend your whole life studying this example. It's beautiful. So if you look at the course description, I said that one of the prerequisites for the course was statistical physics. Here's why. Here's why. We said that classical many-body systems, consider a classical many-body system in equilibrium in d+1 spatial dimension. Okay? So we have d+1 spatial dimension, classical many-body system in equilibrium. We said that if you take the long wavelength limit, continuum limit of that, you get a classical field theory in equilibrium in d+1 spatial dimensions. Okay, are we good? We're going to go through an example of this. Now here comes a new bit. There's something called quantum classical field theory correspondence. A classical field theory at finite temperature in equilibrium in d+1 spatial dimension is equivalent to a Euclidean quantum field theory in d+1 space-time dimension. So you trade one dimension of space for quantum. The cost of quantum is one dimension of space. Going from classical to quantum, you have to pay off your tax, one dimension space. This is something rigorous, but the catch is Euclidean quantum field. Now, we won't discuss it in the class, but one way to axiomatically approach quantum field theory, we'll not discuss it in this class, but historically that was one of the main reasons, one of the most important, most promising approaches was to define relativistic quantum field theory as the analytic continuation of Euclidean quantum field theory by sending Euclidean time to IT. All right, I said what I said. This is a long story. You could spend your whole life on it. I just want to mention, I want you guys to have heard the terminology of quantum classical field correspondence. All I want from you for this example, so this is not the example yet. The example is what follows below. All right. But the example is just supposed to exemplify one such thing. And along the way, we're going to discover the relevance of functional integrals, otherwise known as passive. Functional integrals. We're going to discover that. We already dealt with functional derivatives. Now we're going to talk about functional derivatives. Take classical Ising model in two spatial dimensions in equilibrium. So here's Ising model. Your degrees of freedom are a bunch of spins up or down, right? So the degrees of freedom are a bunch of spins up or down, up or down. They're sitting on at each vertex. Your Hamiltonian is just nearest neighbor. Ij bracket means that they're nearest neighbor. Just Si dot Sj. So there's a cost if they are, there's an energy cost if they are not aligned, right? Okay. So what does it mean to say you are at finite temperature in equilibrium? It means that you should consider the partition function. What is the partition function? It's the sum. Oh, sorry. You have a Hamiltonian. Hamiltonian is a functional from, or function from state configuration. So each state configuration, configuration up, down, up, down, up, down, that's, we're going to call a microstate, right? So Hamiltonian is a map from microstates to numbers, energy. If you did take a continuum limit, it would be a functional, but we haven't taken the continuum limit yet, okay? All right, so for each configurations of S, so this curly S means the set of all possible configurations, right? You have to write down e to minus h of that configuration divided by the temperature, and you have to sum over all configurations. That's what the partition function is. So to each, what we are doing is this. To each microstate, we associate an unnormalized probability, e to minus h of s, h, a relative probability, and we're summing over all microstates. That's what the partition function is. Are we good? Are you with me so far? Very good. Next, we're going to follow the philosophy of this course. I'm just going to squint. My eyes are not good. I'm going to look at low energy. I'm just going to zoom out. So what I'm going to do is that I'm going to do spin blocking. I'm going to take my lattice and split it into big chunks, big squares. And because I cannot, my glasses are bad, my eyes are bad, I cannot resolve within each box. I can replace the degrees of freedom within each box with their average. So if I have 4 spins up, the average would be 1. Say my box is 4 sides. If 2 is up, 2 is down, that's 0. If it's like, you know, that there, I have, I guess, 4 different values between 1 and minus 1. Right? So this is the average degree of freedom. Now, I have a notion of a macro state. As someone with bad eyes, all I see is macro states, and each macro state has a fixed value here, 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 here in these big boxes, but each macro state is comprised of a whole bunch of microstates. Is this clear? Right? For example, the macro state 0 for 4 spins, right, could be this, could be this, could be this, I don't know, this, right? These are microstates that contribute to that macro state. There are a whole bunch of them. Now, what I do next is I take my partition function, which had a sum over all microstates, and split the sum into 2 parts. Sum over macrostates, and then sum over all the microstates that contribute to that particular macrostate. Now, what I'm gonna do is I'm gonna construct a partition function for the guy with the bad eyes, right? So partition function for the guy with the bad eyes is basically you have to do this sum for each value, for each configuration, coarse grain configurations, they're called coarse grain. For each coarse grain configuration, you calculate this, take the log of it and stick it in there, right? So I just defined the partition function for the guy with bad eyes. Now, deep in the low energy, in the very, very infrared regime, because these are averages, your boxes get larger and larger, right? If you had n spins between in your box, now the values of spin, the values of the average are becoming closer and closer to continuous. As you take the continuum limit, you basically have your m becomes a continuous function, smoothly varying function in low energies. So m of x becomes a function. Now you have to sum over all these functions. What is this? This is a functional integral. Your sum becomes an integral, but it's a functional integral, right? So your partition function becomes a functional integral over e to minus beta, right? Inverse temperature, f of m. F is this, I guess, action function, the local part of the action function, Hamiltonian for the guy with the bad eyes, right? This is free energy, right? Coarse grade free energy. Now, this is nothing but the very definition of what we call Euclidean quantum field theory in one lower dimension. All right, so let me just, because we're running out of time, let me just summarize quickly and then I'll pause for questions. What did we do? In the last lecture, we described the equations of motion of classical field theory. Euler-Lagrange equation, we talked about differentiation for functionals because there was the action principle that was the basis of our thing. Two things that we've been dealing a lot with has been the assumption of locality and the assumption of Poincare invariance, right? So we went through 4 examples in this lecture. We went through massive free bosons, relativistic free bosons. The thing to remember, you get the Klein-Gordon equation as your Euler-Lagrange equation. The solutions are plane wave, and the on-shell condition is the dispersion relation. The non-relativistic case, you do the same thing. The action is first order in time derivatives. The equations formally look like Schrodinger equation, but they are not. Physically, the interpretation is different because it's classical. Solutions are plane wave with dispersion that's relativistic. Sorry, non-relativistic. Dispersion that's non-relativistic, but there are no negative frequency modes. Example 3 was Maxwell equations. This is the elegant relativistic way of writing down Maxwell equations. We wrote down everything in terms of an action principle. It was local, everything was good, but it came at the cost of introducing a whole bunch of redundancies. That is what's called gauge redundancies. And it's intimately tied to the charge conservation. Statistical field theory was our example number 4. This is a setup where I was studying field theory. I was studying some classical system in equilibrium, and I happened to be near a phase transition where the correlation length is large. So I had to look at very, very long distance. I had to coarse grain on very, very long distances. And in that regime, I ended up viewing my partition function, my coarse grade partition function for low energy modes as a functional integral, over field configurations, smooth field configurations, which I just said in words. This is the very definition of Euclidean quantum field theory in one lower dimension. That's all. All right. Any questions? Again, perhaps it was either super clear or super vague, but we're gonna let that go. All right, if there are no questions, thank you so much. Of course, you can always ask questions on Slack. I'll post this, and thank you so much. Bye, guys.
Thank you.